Chapter 3 Hypothesis Testing. Chapter 2 showed how a statistic such as the mean of a sample can be used to estimate a parameter, such as the mean of a population, with a known degree of confidence. This is an important use of inferential statistics, but a more important use is hypothesis testing. Hypothesis testing may seem complex at first, but the steps involved are actually very simple. To test a hypothesis about a mean, the steps are as follows. 1. State the null and alternative hypothesis. This would be the H0 and HA. Select the decision criterion alpha or level of significance. Establish the critical values. Then, draw a random sample from the population and calculate the mean of that sample. Next, calculate the standard deviation S and estimated standard error of the sample Sx. Next, calculate the value of the test statistic t that corresponds to the mean of the sample tcalc. And finally, compare the calculated value of t with the critical values of t and then accept or reject the null hypothesis. Step 1. State the null and alternative hypothesis. Consider the following example. The dean of a medical school states that the school students are a highly intelligent group with an average IQ of 135. This claim is a hypothesis that can be tested. It is called the null hypothesis, or H0. It has this name because in most research, it is the hypothesis of no difference between samples or populations being compared. For example, that a new drug produces no change compared with a placebo. If this hypothesis is rejected as false, then there is an alternative or experimental hypothesis, HA, that logically must be accepted. In the case of the dean's claim, the following hypothesis can be stated. Null hypothesis H0, where mu is equal to 135. And the alternative hypothesis is HA, where mu is not equal to 135. One way of testing the null hypothesis would be to measure the IQ of every student in the school. In other words, to test the entire population, but this would be expensive and time-consuming. It would be more practical to draw a random sample of students, find their mean IQ, and then make an inference from this sample. Step 2. Select the decision criteria alpha. If the null hypothesis were correct, would the mean IQ of the sample students be expected to be exactly 135? No, of course not. As shown in Chapter 2, sampling error will always cause the mean of the sample to deviate from the mean of the population. For example, if the mean IQ of the sample were 134, we might reasonably conclude that the null hypothesis was not contradicted, because sampling error would easily permit a sample with this mean to have been drawn from a population with a mean of 135. To reach a conclusion about the null hypothesis, we must therefore decide at what point is the difference between a sample mean and 135 not due to chance, but due to the fact that the population mean is not really 135 as the null hypothesis claims. This point must be set before the sample is drawn and the data are collected. Instead of setting it in terms of the actual IQ score, it is set in terms of probability. The probability level at which it is decided that the null hypothesis is incorrect constitutes a criterion, or a significance level known as alpha. As the random sampling distribution of means showed in figure 2.2, it is unlikely that a random sample mean will be very different from the true population mean. It is very different, lying far toward one of the trials of the curve. If it is very different, lying far toward one of the tails of the curve, it arouses suspicion that a sample was not drawn from the population specified in the null hypothesis, but from a different population. If a coin were tossed repeatedly and 5, 10, or 20 heads occur in a row, we would start to question the unstated assumption or null hypothesis that it was a fair coin, i.e., 8-0 is, is where heads is equal to tails. In other words, the greater the difference between the sample mean and the population mean specified by the null hypothesis, the less probable it is that the sample really does come from the specified population. When this probability is very low, we can conclude that the null hypothesis is incorrect. How low does this probability need to be for the null hypothesis to be rejected as incorrect? By convention, the null hypothesis will be rejected if the probability that the sample mean could have come from the hypothesized population is less than or equal to 0.05. Thus, the conventional level of alpha is 0.05. Conversely, if the probability of obtaining the sample mean is greater than 0.05, the null hypothesis will be accepted as correct. Although alpha may be set lower than the conventional 0.05 for reasons which will be shown later, it may not normally be set any higher than this. Step 3. Establish the critical values. In Chapter 2, we saw that if a very large number of random samples are taken from any population, their means form a normal distribution, the random sampling distribution of means, that has a mean of mu subscript x. That has a mean equal to the population mean, which is mu. We also saw that we can specify the values of random sample means that are so high or so low that these means would occur in only 5% or fewer of all possible random samples. This ability can now be put to use because the problem of testing the null hypothesis about the student's mean IQ involves stating that random sample means are so high or so low that they would occur in only 5% or fewer of all random samples that could be drawn from a population with a mean of 135. If the sample means falls inside the range within which we would expect 95% of random sample means to fall, the null hypothesis is accepted. This range is therefore called the area of acceptance. If the sample mean falls outside this range in the area of rejection, the null hypothesis is rejected and the alternative hypothesis is accepted. The limits of this range are called the critical values, and they are established by referring to the table of t-scores. In the current example, the following values can be calculated. The sample size is 10, so there are n minus 1, which is equal to 10 minus 1 equals 9 degrees of freedom. The table of t-scores in table 2.1 shows that when df is equal to 9, the value of t that divides the 95% or 0.95 area of acceptance from the 2.5% or 0.025 areas of rejections is plus or minus 2.262. These are the critical values, which are written the t criticals is equal to plus minus 2.262. Figure 3.1 shows the random sampling distribution of means for our hypothesized population with a mean of 135. It also shows the areas of rejection and acceptance defined by the critical values of t that were just established. As shown, the hypothesized population mean is sometimes written mu with a subscript of hype. Here's a figure 3.1 and random sampling showing random sampling distribution of means for a hypothesized population with a mean of 135. You have frequency on the y-axis and the t-score on the x-axis. 0 is in the middle here. And then you can see all the positive and the negative values. And there's the mean. This is 95% of the area of acceptance of a certain hypothesis. And the outliers are what we reject. We have now established the following: the null and alternative hypotheses. We've established the criterion that will determine when the null hypothesis will be accepted or rejected, and the critical values of t associated with this criterion. A random sample of students can now be drawn from the population. The t-scores or tcalc associated with their mean IQ can then be calculated and compared with the critical values of t. This is a t-test, a very common test in medical literature. Step 4. Draw a random sample from the population and calculate the mean of that sample. So a random sample of 10 students is drawn. Their IQs are as follows: 115, 140, 133, 125, 120, 126, 136, 124, 132, and 129. And the mean of this sample is 128. So step 5, calculate the standard deviation and estimated standard error of the sample. So, to calculate the t-score corresponding to the sample mean, the estimated standard error must first be found. This is done as described in Chapter 2. The standard deviation of this sample is calculated and found to be 7.542. The estimated standard error is then calculated as follows. Standard errors is equal to standard deviation divided by the square root of the total number. And when we plug in these numbers, which would be 7.542 with the square root divided by the square root of 10, you get 2.385. Step 6. Calculate the value of t that corresponds to the mean of the sample tcalc. Now that the estimated standard error has been determined, the t-score corresponding to the sample mean can be found. It is the number of estimated standard errors by which the sample mean lies above or below the hypothesized population mean. So the t-score can be calculated by taking the mean and subtracting the mu hypothesized, and dividing that by S of x, and plugging in those numbers gives you negative 2.935. So the sample mean 128 lies approximately 2.9 estimated standard deviation errors or standard errors below the hypothesized population means of 135. Step 7. Compare the calculated value of the t with the critical values of t, and then accept or reject the null hypothesis. If the calculated value of t associated with the sample mean falls at or beyond either of the critical values, it is within one of the two areas of rejection. Figure 3.2 shows that the t-score in this example does fall within the lower area of rejection. Therefore, the null hypothesis is rejected, and the alternative hypothesis is accepted. The reasoning behind this is as follows. The sample mean differs so much from the hypothesized population mean that the probability that it would have been obtained if the null hypothesis were true is only 0.05 or less. Because this probability is so low, we conclude that the population mean is not 135. We can say that the difference between the sample mean and the hypothesized population mean is statistically significant, and the null hypothesis is rejected at the 0.05 level. This would typically be reported as follows. The hypothesis that the mean IQ of the population is 135 was rejected, and t is equal to negative 2.935, and df is equal to 9, with p less than or equal to 0.05. So here's a plot showing the critical values of t for the exception or rejection of H0. Okay. If, on the other hand, the calculated value of t associated with the sample mean fell between the two critical values in the area of acceptance, the null hypothesis would be accepted. In such a case, it would be said that the difference between the sample mean and the hypothesized population mean failed to reach statistical significance. P was greater than 0.05. Z-tests. References to a z-test are sometimes made in medical literature. A z-test involves the same steps as a t-test and can be used when the sample is large enough, meaning n is greater than 100 for the sample standard deviation, to provide a reliable estimate of the standard error. Although there are situations in which a t-test can be used but a z-test cannot, there are no situations in which a z-test can be used but a t-test cannot. Therefore, t-tests are the more important and widely used of the two. The meaning of statistical significance. Here's a high yield point. When the result is reported to be significant at p less than or equal to 0.05, it merely means that the result was unlikely to have occurred by chance. In this case, that the likelihood of the result having occurred by chance is 0.05 or less. This does not necessarily mean that the result is truly significant in the everyday meaning of the word, that it is important, noteworthy, or meaningful. Nor does it mean that it is necessarily clinically significant. In the previous example, if the mean IQ of the sample of students were found to be 134, it is possible, if the sample were large enough, that this mean could fall in the area of rejection, and so the null hypothesis mu equal 135 could be rejected. However, this would scarcely be an important or noteworthy disproof of the dean's claim about the student's intelligence. In fact, virtually any null hypothesis can be rejected if the sample is sufficiently large, because there will almost always be some trivial difference between the hypothesized mean and the sample mean. Studies using extremely large samples, therefore, risk producing findings that are statistically significant but otherwise insignificant. For example, a study of an antihypertensive drug versus a placebo might conclude that the drug was effective, but that if the difference in blood pressure was only 1 millimeters of mercury, this would not be a significant finding in the usual meaning of the word and would not lead physicians to prescribe the drug. Type 1 and Type 2 errors. A statement that a result is significant at p less than or equal to 0.05 means that an investigator can be 95% sure that the result was not obtained by chance. It also means that there is a 5% probability that the result could have been obtained by chance. Although the null hypothesis is being rejected, it could still be true. There remains a 5% chance that the data did in fact come from the population specified by the null hypothesis. Another high yield point, questions on type 1 and 2 errors will appear not only on step 1 but also on step 2 and step 3, and even specialty board certification examinations, so we'd best learn it cold. Right. Accepting the alternative or experimental hypothesis when it is false is a type 1 or false positive error. A positive conclusion has been reached about a hypothesis that is actually false. The probability that a type 1 error is being made is in fact the value of p, because this value relates to the criterion alpha. A type 1 error is also known as an alpha error. The opposite kind of error, rejecting the alternative or experimental hypothesis when it is true, is a type 2 or false negative error. A negative conclusion has been drawn about a hypothesis that is actually true. This is also known as a beta error. While the probability of making type 1 error is alpha, the probability of making a type 2 error is beta. Table 3.1 shows the 4 possible kinds of decisions that can be made on the basis of statistical tests. I see. The choice of an appropriate level for the criterion alpha therefore depends on the relative consequences of making a type 1 or type 2 error. For example, if a study is expensive and time-consuming and is therefore unlikely to be repeated, yet has important practical implications, the researchers may wish to establish a more stringent level of alpha, such as 0.01, 0.005, or even 0.001, to be more than 95% sure that their conclusions are correct. This was done in the multi-million-dollar Lipid Research Clinic's coronary primary prevention trial in 1979, whose planners stated that since the time, magnitude, and costs of the studies make it unlikely that it could ever be repeated, it was essential that any observed benefit of total cholesterol lowering was a real one. Therefore, alpha was set to 0.01 rather than the usual 0.05. Although the criterion to be selected need not be 0.05, by convention it cannot be any higher. Results that do not quite reach the 0.05 level of probability are sometimes reported to approach significance or to show statistically significant trends, phrases that perhaps reveal the investigator's desire to find statistical significance. If no such desire was present, the result would more likely simply be reported as non-significant or NS. Many researchers do not state a predetermined criterion or report their results in terms of one. Instead, they report the actual probability that the obtained result could have occurred by chance if the null hypothesis were true. For example, p is equal to 0.015. In these cases, the p-value is more an index of rarity than a true decision criterion. The researchers are showing how unlikely it is that a type 1 error has been made, even though they would have still rejected the null hypothesis if the outcome were only significant at the 0.05 level. Power of statistical tests. Although it is possible to guard against a type 1 error simply by using a more stringent, lower level of alpha, preventing a type 2 error is not so easy, because a type 2 error involves accepting a false null hypothesis. The ability of a statistical test to avoid a type 2 error depends on its ability to detect a null hypothesis that is false. A high yield point to remember is that this ability is called the power of the test and is equal to 1 minus beta. It is the probability that a false null hypothesis will be rejected. Conventionally, a study is required to have a power of 0.8 or a beta of 0.2 to be acceptable. In other words, a study that has a less than 80% chance of detecting a false null hypothesis is generally judged to be unacceptable. Calculating beta and determining the power of a test is complex. Nevertheless, it is clear that a test's power or ability to detect a false null hypothesis will increase as alpha increases, for example, from 0.01 to 0.05. This will make the critical values of t less extreme, thus increasing the size of the areas of rejection and making rejection of the null hypothesis more likely. There will always be a trade-off between type 1 and type 2 errors. Increasing alpha reduces the chance of a type 2 error, but it simultaneously increases the chance of a type 1 error. The size of the difference between the sample mean and the hypothesized population mean increases. This is known as the effect size. In the preceding example, a difference between a hypothesized population mean IQ of 135 and a sample mean IQ of 100 would be detected much more easily, and hence the null hypothesis would be rejected more easily than the difference between the hypothesized IQ of 135 and the sample mean IQ of 128. The larger the difference, the more extreme the calculated value of t. In clinical trials, the effect size is a difference that would be clinically important, or the difference that is expected to occur between two groups in the trial, such as a difference in systolic blood pressure of 10 millimeters of mercury between a new antihypertensive drug and a placebo. Ideally, all studies of report acceptance of the null hypothesis should also report the power of the test used so that the risk of a type 2 error is made clear. Sampling error decreases. A lower sampling error means that the sample's standard deviation is reduced, which will cause the estimated standard error to be lower. Because t is calculated in terms of estimated standard errors, this will make the calculated value of t more extreme, whether in a positive or negative direction, increasing the likelihood that it falls in one of the areas of rejection. The sample size n increases. This reduces the estimated standard error, thereby increasing the calculated value of t. Therefore, a large-scale study is more likely to detect a false null hypothesis, particularly if the effect size is small, than a small-scale study. For example, if a coin is tossed 1,000 times, resulting in 600 heads and 400 tails, it is much easier to reject the null hypothesis that the coin is a fair one than if the coin is tossed 10 times and 6 heads and 4 tails are obtained. A key high yield point: increasing the sample size is the most practical and important way of increasing the power of a statistical test. The findings of a study in which the null hypothesis is accepted may be disputed by researchers who may argue that the study's sample was too small to detect a real difference or effect. They may replicate the study using a larger sample to improve the likelihood of getting statistically significant results that will allow them to reject the null hypothesis. Determining the size of the sample that needs to be used is crucial. A sample that is too small may be unable to answer the research question due to a lack of power, but one that is too large is wasteful of scarce resources. Researchers calculate the required sample size by means of a formula that incorporates the risk of a type 1 error, alpha, or the p-value required to reject the null hypothesis, usually 0.05, the risk of a type 2 error, the power of the statistical test, usually 80% or 0.80, the variability of the data, and the effect size. Once again, it is clear that a larger sample is required to look for small or subtle effects than for large or obvious ones. The concept of power can be explained using the example of a military radar system that is being used to detect a possible impending air attack. The null hypothesis is that there are no aircraft or missiles approaching. The alternative hypothesis is that they are. Clearly, a powerful radar system is going to be more able to detect intruders than is a weak one. What if the radar system is functioning at a very low power and the operators are not aware of this fact? They watch their screens and report that the null hypothesis is correct. There are no aircraft or missiles approaching, but the power of their system is so low that they are in great danger of making a type 2 or false negative error. This danger is greater if the effect size, the difference between the presence or absence of impending attackers, is likely to be low. A single light aircraft will be detected only by a very powerful system, while a low-powered system may be adequate to detect a squadron of large bombers. So, just as with a statistical test, the more subtle the phenomena being tested for, the more powerful the test needs to be. On the other hand, a very powerful system, like a very powerful statistical test, runs the risk of making a type 1 error, a phenomenon so subtle as to be trivial, such as a flock of birds may produce a signal, which may lead the operators to reject the null hypothesis and conclude that the null hypothesis is directional hypotheses. So far, we have used the example of a non-directional alternative hypothesis, which merely stated that the population mean is not equal to 135, but did not specify whether the population mean is above or below this figure. This was appropriate because the medical school dean claimed that the student's mean IQ was 135. His claim, which constitutes the null hypothesis, could legitimately be rejected if the sample mean IQ turned out to be significantly above or below 135. Therefore, as figure 3.2 showed, there were two areas of rejection, one above the mu hypothesis and one below. What if the dean had instead claimed that the student's average IQ was at least 135? This claim could only be rejected if the sample mean IQ turned out to be significantly lower than 135. The null hypothesis is now mu is greater or less than 135, and the alternative hypothesis must now be mu is less than 135. The alternative hypothesis is now a directional one, which specifies that the population mean lies in a particular direction with respect to the null hypothesis. In this kind of situation, there are no longer two areas of rejection on the random sampling distribution of means. As figure 3.3 shows, there is now only one. If alpha remains at 0.5, the area of acceptance, the area in which 95% of the means of possible samples drawn from the hypothesized population lie, now extends down from the very top end of the distribution, leaving just one area of rejection. The bottom 5% of the curve, the area of rejection, now lies only in one tail of the distribution rather than in both tails. The steps involved in conducting a t-test of this directional null hypothesis are exactly the same as before, except that a critical value of t is now different. The critical value now divides the bottom 5% tail of distribution from the upper 95%. Instead of dividing the middle 95% from two tails of 2.5% each, the appropriate column of table 2.1 shows that the new critical value of t for the same df of 9 is negative 1.833 rather than the previous value of plus minus 2.262. As figure 3.3 shows, this new critical value is associated with only one tail of the distribution. Using this value, therefore, involves performing a one-tailed or one-sided statistical test. Because the alternative hypothesis is directional, previously, when the alternative hypothesis was non-directional, the test performed was a two-tailed or two-sided test. The critical value of t is less extreme for the one-tailed test than for the two-tailed test. Consequently, when a one-tailed test is used, a less extreme sample mean can exceed the critical value and falls within the area of rejection, leading to rejection of the null hypothesis. As a result of this, one-tailed tests are more powerful than two-tailed tests. For example, if the mean IQ of the sample of 10 students were 130 instead of 128, with the same standard deviation of 7.542, the same estimated standard error of 2.385 as before, the value of t corresponding to this mean would be 130 minus 135 divided by 2.385, which equals negative 2.096. This score falls within the area of acceptance for two-tailed test, but it falls within the area of rejection for a one-tailed test, as shown in figure 3.3. The dean's claim could therefore potentially be accepted or rejected, depending on how it is interpreted and which test is consequently performed. As this example shows, a researcher who wishes to reject the null hypothesis may sometimes find that using a one-tailed rather than a two-tailed tests allows a previously non-significant result to become significant. For this reason, it is important that one-tailed tests are only performed under the correct conditions. The decision to use a one-tailed test must depend on the nature of the hypothesis being tested and should therefore be decided at the outset of the research rather than being decided afterwards according to how the results turn out. One-tailed tests can only be used when there is a directional alternative hypothesis. This means that they may not be used unless results in only one direction are of interest, and the possibility of the results being in the opposite direction is of no interest or consequence to the researcher. When testing a new drug, the normal null hypothesis is that the drug has no effect, so it will be rejected if the drug turns out to have an effect too great to be due to chance. regardless of whether the effect is a positive one or a negative one. Although the researcher expects the drug to produce an improvement in the patient's clinical state, this expectation does not permit the use of a directional alternative hypothesis. The researcher can do this only if it is of no interest or consequence if the drug actually makes patients worse, which is not usually the case in medical research. The main exception to this is in non-inferiority trials. Testing for differences between groups. We have seen how a t-test can be used to test a hypothesis about a single mean. However, biomedical research is typically more complex than this. Researchers commonly want to compare two means, such as the effects of two different drugs or the mean survival times of patients receiving two different treatments. A slightly more complex version of the t-test can be used to test for a significant difference between two means. The null hypothesis is that the two groups, A and B, were drawn from a populations with the same mean. In other words, that the two samples were in effect drawn from the same population and that there is no difference between them. The alternative hypothesis is that the two population means are different. The null hypothesis, meaning that mu A is equal to mu B, and the alternative hypothesis being that mu A is not equal to mu B. Post hoc testing and subgroup analyses. When hypotheses exist about different groups of patients, such as according to their gender or disease severity, a subgroup analysis of the differences between several means will be done. For example, researchers studying a new antihypertensive medication may hypothesize that patients with high renin levels or obese patients may respond better than those with low renin levels or non-obese patients. When these hypotheses are pre-specified, these tests are legitimate. However, it is common for researchers to test hypotheses that were not pre-specified at the start of the research program. This is post hoc hypothesis testing. Post hoc subgroup analysis might appear to show that a medication significantly reduces blood pressure among men but not among women, among diabetic patients rather than non diabetic patients, and among patients in US research centers rather than those in European ones, or perhaps that it reduces headaches, edema, or urinary frequency, and so on. With computerized data, it is easy to perform innumerable subgroup analyses. Clearly, this is hazardous. If each of these tests uses an alpha of 0.05, then multiple tests are highly prone to at least one type 1 error, erroneously rejecting the null hypothesis that the medication is ineffective. Even if the null hypothesis is actually true for every test that is done, the probability of producing at least one type 1 error is zero point 0.4 when 10 tests with an alpha of 0.05 are done. With 20 tests, the risk is 0.64. Especially when the commercial or academic stakes are high, it is tempting to perform multiple post hoc subgroup analysis and then to report only those that are statistically significant, leaving the reader unable to determine whether these are merely the false positive tips of the iceberg or a larger number of tests that did not attain significance. The risk of type 1 errors is true whether the multiple subgroup analyses are pre-specified or post hoc. But when they are pre-specified, the researchers at least had a pre-existing rationale for the hypothesis. In an effort to establish exactly what hypotheses will be tested prior to data collection, and to reduce selective reporting of only favorable results, the International Committee of Medical Journal Editors requires that studies are pre-registered prior to data collection, and that this registration includes a statement of the study hypotheses and primary and secondary outcome measures. Some memorable post hoc subgroup analysis findings that have been criticized as probable type 1 errors, according to slide 2000 study, include a report that diabetes is commoner among boys born in October than in other months. Hmm. A report that lung cancer is more common among people born in March than in other months. An analysis of the second international study of infarct survival, ISIS-2, which showed that aspirin had markedly beneficial effect on heart attacks patients unless the patient happened to be born under the Gemini or Libra astrological birth signs. Subgroup analyses are also at risk for type 2 errors, as the sample sizes in each of the subgroups may not be large enough for the test to have significant power to reject a false null hypothesis. In general, subgroup analysis should be considered only as starting points for further research, rather than conclusive in their own right, especially when they are based on post hoc analyses. Subgroup effects are sometimes said to be the result of effect modification or interaction. For example, a randomized control trial of a new drug may find that it has no effect on the risk of diabetes, but a subgroup analysis of the data may show that it apparently increases the risk of diabetes among men, but reduces it among women. In this case, gender is an effect modifier, a factor that influences the effect of the phenomenon, such as risk of diabetes that is being studied. But it does so differently in different subgroups, men versus women, in a way that can only be seen after the data have been obtained. In this situation, the division of participants into men and women may be termed stratification. This post hoc stratification or stratified analysis differs from the stratification, sometimes called pre stratification, which may be done during the design phase of the study to prevent confounding. Effect modifiers are felt to be real biological effects, which we want to understand, unlike confounders, which are artifacts of poor study design and which we want to eliminate. This example also demonstrates the concept of interaction, the interdependent operation of two or more biological causes to produce, prevent, or control an effect. In this case, the drug and the patient's gender interacted to produce an effect on the risk of diabetes. The whole was different from the sum of the parts. This would be called a drug times gender interaction. Non-parametric, non-parametric and distribution-free tests. The previous sections have dealt with testing hypotheses about means using the T and Z tests. These tests share three common features. Their hypotheses refer to a population parameter, the population mean. For this reason, such tests are called parametric tests. Their hypotheses concern interval or ratio scale data, such as weight, blood pressure, IQ, per capita income, measures of clinical improvement, and so on. They make certain assumptions about the distribution of the data of interest in the population, principally that the population data are normally distributed. As was shown earlier, the central limit theorem allows this assumption to be made, even when little is known about the population distribution, provided that random samples of sufficient size are used. There are other statistical techniques that do not share these features. They do not test hypotheses concerning parameters, so they are known as nonparametric tests. They do not assume that the population is normally distributed, so they are also called distribution-free tests. They are used to test nominal or ordinal scale data. Such tests, however, have the disadvantage that they are generally less powerful than parametric tests. Chi-square. The most important non-parametric test is the chi-square test, which is used for testing hypotheses about nominal scale data. Chi-square is basically a test of proportions, telling us whether the proportions of observations falling in different categories differ significantly from those that would be expected by chance. For example, in tossing a coin 100 times, we would expect about 50% or 50 of the tosses to fall in the category of heads and 50% to fall in the category of tails. If the result is 59 heads and 41 tails, chi-square would show whether this difference in proportion is too large to be expected by chance, that is, whether it is statistically significant. As with other tests, chi-square involves calculating the test statistic according to a standard formula and comparing it with the critical value appropriate for the level of alpha selected shown in the published chi-square tables, which can be found in most books, in most statistics textbooks. Chi-square is also used in more complicated nominal scale questions. For example, a study might compare the rates of microbiologic cure for 3 different antibiotics used for urinary tract infections, as shown in Table 3.2. This kind of table is a contingency table, which is the usual way of presenting this kind of data. It expresses the idea that one variable, such as cure versus lack of cure, may be contingent on the other variable, such as which antibiotic a patient took. The question that chi-square can answer is this: is there a relationship between which antibiotic the patient took and achieving a microbiologic cure? So here's table 3.2, telling us the number of patients achieving a microbiological cure by antibiotic. We have 3 different antibiotics on the top, and on the left we have the number achieving cure and the ones that do not achieve the cure. Okay. So it seems that there is a relationship.